and not too much, but you can find it some places. I was just mentioning that here in SWCC in Jubail, they have a once-through MSF system, which is used as a pilot plant, so that they use it for testing if they need to try a new anti-scalant, for example, they use it there. If they need to apply some new technologies or try some experimentation, they use it for that purpose, so that they do not disturb their production. And it's not a small unit, by the way. It's producing something like 20 cubic meters per day, which is it's not a lab scale. It's definitely some sort of a miniature model of a true or a large scale unit. Lately, companies like Doosan, which is a very well-known Korean companies, it has so many business branches. One of them is desalination, and in the last few years, it was trying to come back again to the once-through system. And the reasons for that were basically that the chemicals that are used for pre-treatment of the water are cheap now compared to what used to be in 30 to 40 years. Accordingly, it's not a waste of resources by using chemicals for these units, and after which the chemicals are rejected to the sea with the brine, with the rejected brine. Previously, it was expensive and people were worried about losing some of the resources just after a single use like that. That's why they thought of recycling the brine. But now the chemicals are getting cheaper. This way, they avoid the utilization of very large brine recycling pump. And the units in that sense can also be some sort of a units with controlled size. What we see here is a reminder of the single stage unit. Numbers are here to remind you again of what used to happen. We have a combination of feed water and cooling water getting into the tubes in a heat recovery process, so that they are going to be used for condensing the vapor that will flash here. The vapor will condense on the outside surface of the tubes. The vapor will be converted into liquid distillate product. And this stream of M. feed and M. cooling water is going to heat up from this temperature of 30 to a higher temperature. This higher temperature is not high. Going from 30 to 35 is not a big deal. But in reality, it's not a single stage. It's multi-stages. If you're going to have in multi-stages, each stage you have a temperature increase of about 3 to 5 degrees, and you have 20 stages, for example, then you are talking about a temperature that's going to enter at 30 and leave the heat recovery part at 90, which is considerably high. And this is good enough for it to operate. Anyway, here, because of it's a single stage, it's only a 5 degrees temperature difference. Here we used additional M. cooling water. And the M. cooling water that is admitted here, it's enough quantity to make sure that all the vapor is going to condense. After utilizing it and condensing the vapor, this water is returned back again to the sea. It's a substantial quantity, 104 kilogram per second, just to produce 1 kilogram per second of distillate. And then the remainder, which is the feed, about 11.5 kilograms per second of seawater is going to enter to this mainly shell and tube heat exchanger, which is what we call the brine heater. And the brine heater heats the water from this value of 35 up to the top brine temperature, which is about 90 degrees centigrade. Heating is done by introducing steam coming from a power plant or a boiler to heat the water. The steam is going to condense and returns back to the power plant. The hot water at top brine temperature is going to enter into a lower pressure stage, so flashing is going to occur. The vapor will rise to condense, as I mentioned earlier, and the condensate will be collected as a product, whereas the brine that will not evaporate, it will be rejected as a rejected brine to the surroundings. This is basically what we have here. When I'm talking about a multi-stage once-through system, I'm replicating this. We are repeating this stage. Instead of a single stage, it will be 20, 30, 40 stages. And by the way, 40 stages is not a huge number, because that used to be sometimes a model for production. You're producing a multi-stage flash desalination system with 43 stages, for example. So the drawback that we have, maybe what I just forgot to mention here, that this system that we see here, when we did the analysis using like engineering equation solver, we found out that the PR, the performance ratio of the system, is about 0.83 or 0.85, which is less than the SEE, or the single effect evaporation. Now, this low performance is going to be replaced or going to be improved by having a brine heater plus n number of stages, which is looking like this. We have a certain number of stages, which is a large number. The seawater is going to enter here at a certain rate, which is basically, you would not need to have additional seawater in. The m dot feed is going to be enough. And the m dot feed is going to be used for condensing this vapor here, and it will condense the vapor several times. Why several times? Because the seawater here enters at a temperature 30, and then it increases here from 30, say to 33, and then from 33 to 36, and then from 36 to 39 to 42 to 45, and so on. Then it leaves at a temperature of about 90, or maybe in this case it will leave at, if we're talking about 20 stages, and each stage has a delta T of 2, so 40 plus 30, 70, and then you heat it here from 70 to 90. When the temperature here of the seawater increases from 32 or 33, the vapor which is coming at 40 degrees centigrade. So always the vapor is at a higher temperature compared to this liquid, and condensation accordingly occurs. Here, the vapor is at a higher temperature of this. If the vapor here is 40, here it will be at about 43 to 45. Here it will be about 48 to 50. Here it will be like 53 to 55. So always the vapor is at a higher temperature compared to the seawater passing inside the tubes. Accordingly, you would expect condensation to occur in every one of these stages in the heat recovery section, which is the top section of every stage. So heat recovery is going to occur, temperature enter is here at 70, and then it will keep on heating until a temperature of about maybe 70, 75. It depends on the effectiveness of the heat recovery process here. And then it is going to enter into the brine heater, where again steam is going to be used to heat this water up to a top brine temperature. Here the top brine temperature is 90. And then it will flash in the first stage. Some vapor will form, it will condense here, and then it will leave this tray to the next stage tray. The part that will not condense is going to be exposed to a pressure reducing process again. Probably weirs can be used for reducing the pressure. So it is going to undergo a pressure reduction process here, so it will enter into an area of a lower pressure. So flashing will occur again. The vapor is going to rise up, whereas the brine which is left is going to go to the next stage, which is also at a lower pressure. So you keep on reducing the pressure from one stage to the other or to the next. Keep flashing occurring from one stage to the next. And you are producing vapor by flashing in every one of these stages. Now you can imagine you have saturated vapor at a temperature of, say, 100. It will enter into an area where the pressure is not 100, but the pressure is 95. So there is an excess temperature here that will result in flashing. and then it will enter into an area of temperature 85, and then 80, and then 75, and then 70, until it reaches for the last stage where the temperature is about 40. So that continuously occurs, and continuously you are having vapor that is going to flash, and as it flashes, it will rise up, it will pass by a mist eliminator, so that no liquid salty water is going to be entrained, and only the vapor is going to rise up and condense and be collected in these trays. And then at the end, you are getting the whole product from these trays here as your M dot. So this is blue arrow, shows how the seawater is going to be heated by recovering some energy. The heating here occurs by the condensing vapor up to the temperature T1 here. After that, it will pass through the brine heater to be heated from T1 to the top brine temperature T node. And after that, it is going to go through flashing, continuous flashing process from a stage to the other, where the temperature is going to drop from T2 or T node, top brine temperature, to Tn, which is the rejected brine temperature, and you're going to reject it back again into the sea. Other than the chemicals that were added to the seawater before it enters here, there was another problem with this once-through systems, which is the temperature of the seawater as it's coming. It's not constant throughout the year. So in summer, it is coming at 30 degrees centigrade. In winter, it might be something like 13 or 15 degrees centigrade, which means that the temperature T1 here will be lower. So you are going to need extra steam so that you can heat it from this lower value of T1 to the same value of T node that we want, which is 90. And that would mean that the performance ratio of the unit can change with change in the seasons. And the recommendation was then we can make use of this kind of systems, the one-through systems, if we are close to the equator, where the temperature is hot all over the year, and which is true. However, there are now some technologies that can be done to overcome this. For example, the brine which is rejected here. If we take this quantity of the brine that is being rejected here and we pass it into a heat exchanger, and the seawater is going to come in winter to be heated up to the required temperature of 30 before it is admitted here, that would be a good option. That would be a good solution for this. So the cost is not high, just making a heat exchanger, but you are going to maintain a constant operation, constant feed temperature to the plant all the time. And that's something that can be done. Layout. Actually, this layout was made by one of our master students back in 2009. He is now a PhD holder, and he works in, I think he's in Essex University in UK. And at that time, we were having like a project, a research project by the DSR, where we wanted to simulate the performance of the MSF once-through system, and then see the effect of a couple of things. What if the value of delta T is controlled to be changed? And the second, what if fouling starts to occur in the brine heater, and how fouling in a brine heater can affect the performance of the whole unit? So that was basically the target of that project. Actually, he made this kind of drawing that we like, to the extent that any paper which is related to the performance of MSF, we use the same figure that has been created at that time. And it is basically showing what would happen in a once-through system. The distillate is being collected continuously in this blue line. It will go to the distillate tank. The rejected brine is going to be rejected, or brine blow down to the sea, whereas the heat recovery section, it receives seawater inlet and it goes through pipes, where after that it's going to go through the brine heater for further heating to the top brine temperature. In once-through MSF systems, brine is not recycled. So that's why it's called once-through. The feed comes to the inlet of the heat recovery section at the last stage. It keeps on going through the pipes, being heated, receiving energy from the steam. After that, it goes through the brine heater to be heated to the maximum temperature, top brine temperature, and then it will go through flashing and flashing and flashing and flashing in every one of the stages, and at the end, it is blown down to the sea again. So there is no reuse of this water. Accordingly, you may not need additional seawater coming in. You don't need seawater to come in and help in the condensation, because the vapor which is formed in every quantity would need a smaller flow rate of the water, which is the feed. Or in other words, the feed is enough to condense all the vapor. As the brine circulates through the stage, its temperature changes, and at the last stage, this is where it is rejected to the sea. We call it the blowdown or the rejected brine state. I will not show this. This was doing some sort of a comparison or an evolution, going from the single stage to the last stage. In this analysis, they combine the whole stages as one and putting it this way, which is actually, it's not really true what's happening here. So I'd rather go through the formal kind of analysis that we do for one through system. This is again a reminder of the temperature distribution in a single stage system where feed seawater enters into the heat recovery section at a temperature T cooling water or T seawater. It is recovering the energy to be heated up to T1, and then it gets into the brine heater where the steam will heat it from T1 to T0, top brine temperature, using steam at temperature Ts. The temperature difference between the steam and the top brine temperature is what we call terminal temperature difference in the hot side or of the brine heater. Then steam is going to condense here, and the brine is heated to the top brine temperature. It will go into the stage where flashing will occur, cooling it down to Tn or Tb. Tb is higher than the vapor by the boiling point elevation. And then the vapor is the one that heats the feed. So that's basically, we have seen that previously in a single stage system. And then that's a little comparison between both of them. The stage is equal to the top brine temperature. For the analysis which is being done, this is an ES program doing the analysis for a one-through system that shows a PR of 0.85, whereas if we are using basically a multi-stage or one-through 6.7, so the PR has increased significantly due to the increase of the number of stages. However, I have to warn you, because in the MSF, the number of stages is not that effective as the MED. We have seen in the MEDs that increasing an effect would almost increase the PR by a value of 1, roughly. Here, this is not the case. Maybe it can increase with the square root of the number of stages, but not with the number of stages. Because the process nature is different here. We rely on flashing. It's not that we are recreating the vapor by by the vapor which is formed in the previous effect, as happens in the MED system. So this is a different system. It seems to us now, when we are looking at the whole picture, that the MED was more effective, which is true. But by the time where this technology has flourished, that was more than 40 years ago, maybe actually it's more than that. It started in 1956, 57, by the first ever commercial unit of MSF that was built in Kuwait. It was built by Westinghouse, by the way. And since 1957, this technology has started and grown up to the last unit that was installed, it was 2014. So we're talking about a substantial amount of decades that passed using this technology. Through this journey from 1950s up to now, there is an issue here, which is at that time, chemicals were not that available. The technology to produce chemical as anti-fouling, anti-scalant, anti-foaming, it was difficult. It was the know-how was not mastered. And then people actually used to use some sort of acid cleaning, and acid cleaning kills the surface of the tubes. It eats the tubes up because it's acid basically, and that makes the lifetime shorter. That's why people were afraid of using the MED, because you are spraying the seawater on the outside surface of the tubes. If you are going to mix the seawater with acid so that you can eliminate or reduce scaling from the outside surface of the tubes, then that used to be a big problem that made people away from the MED for quite a bit of time, until they improved the additives to be added to the system, and then MED expansion started. So that's some sort of how it evolved in history, and that's how the MSF becomes some sort of an iconic kind of technology for desalinating the water. What we noticed here, going from the single stage to the multi-stage, a significant increase in the PR, going from 0.85 to something like 6.7. This is a significant increase. It's more than 10 times, or it's about, or close to 10 times to be fair. It does not need water for heat rejection, so that reduces the needs for very large pumps to be utilized. Still has flow rate of intake seawater. Yes, the flow rate is still higher, but it is not as much as the rate that we have seen for the once through. And accordingly, you made some sort of a saving here. It reduced the flow rate so that you would reduce the pumping power, and that's also serving in our case. Let's go back again to the numbers quickly. For the once through system, look at the flow rate that we have here for the seawater. We are talking about a flow rate of about no, that's the MSF. Look at this one. What I mean here is just looking at the flow rate, 115 kilograms per second. This is a huge quantity, because at the end, what we are looking for is 1 kilogram per second of sweet water. When you go from this to that, you see how much is the quantity that we are adding here in this system. It's only about 11.22. There's no M dot cooling water here. It's basically M dot feed. And you are converting 1 kilogram per second of this into sweet water, and the rest is going to be rejected brine. So M dot feed is equal to M dot distillate plus M dot brine. So we're talking about substantially lower flow rate of the feed compared to the case of the once through. And this is another benefit that we're getting from this unit. This is the layout again, like a third view for the layout of the MSF once through system. And again, the word once through has to do with that there is seawater coming here. It will be heated by heat recovery, and then heated here inside the tubes by the steam, which is in the shell side, and then the hot is going to be flashed and flashed and flashed and then thrown away. So it's coming from the sea, going through the unit and going back again to the sea to be rejected. That's why it's called once through system. On the other hand, what we are not doing here, we are not recycling it. We are not taking this to go back again to the unit. This is the brine recirculation, which is not what we are doing here. The disadvantages, I just mentioned that you cannot control the feed seawater temperature unless you do what I just mentioned a while ago, that you put a heat exchanger here, And this heat exchanger can be used to preheat the seawater before coming in here. Then yeah, you can, at this case, you can control the inlet feed temperature and you will not be affected by the season changes. And by the way, they are doing that in the MED unit, which is located here in Jubail by Marafat company, that use a heat exchanger that they operate only in winter. They don't operate it in summer. In summer, they don't need it. Temperature is already 30. You don't need a temperature more than that because you need some relatively colder seawater coming to condense the vapor. But that's not what's happening with this unit. So the feed seawater temperature, we talked about it already. And in some cases where the temperature variation is large, the performance would change significantly from season to season. That would lead to reduced performance of the whole unit because basically you have to spend more energy to reach for the top brine temperature in one hand. On the other hand, as if we don't do that, if the top brine temperature, we let it be lower. And instead of going to 90, you will accept a top brine temperature of 75. Then, as the condensation occurs, the vapor specific volume value increases a lot, which means that you are going to need substantially bigger size of stages, which is not practical to have. The ratio between the M dot distillate by the M dot feed is a ratio of 1 to 10. If you recall the last figure that we have seen for the OT, we're saying that we have something like about 11.5 kilogram per second flow rate of the seawater, through which you can get 1 kilogram per second of distillate. So it's almost 1 to 10. The brine recirculation, as we will see when we reach to it, it will be 1 to 2.5 only. So there is much less water that we are taken from the sea when we are operating a brine recirculation system. So this ratio enhances in the BR version of the multi-stage flash desalination units. Now, we are looking at typically what you would see at stage number I, for example. Stage number I is receiving seawater from the next stage. Remember that the seawater enters into the last stage, stage number M, and it keeps on flowing inside the tubes until it reaches stage number 1. After that, it goes into the brine heater. So it is coming from Ti plus 1, the M dot feed, and the M dot feed remains constant because it is passing inside the tubes. So when it starts here, it starts as M dot feed. When it reaches here, it reaches as M dot feed also. And at the same salinity because it's not exposed to any dilution or concentration. It's water passing inside the tube all the way across the stages. So it enters as M dot feed and it leaves as M dot feed. It enters to this stage as Ti plus 1 and it leaves as Ti. Which one is higher, by the way? Ti plus 1 or Ti?
Ti.
Ti, yes, because when you are moving in this direction, sorry, the temperature increases. And then the distance coming from the previous stage at TVI, and the difference between TVI and TI is basically the boiling point elevation. It will enter here. Actually, it's the combination of the distillate that has formed in the previous effects. It will come here where it is going to receive an additional quantity of distillate so that it would leave at sigma Di plus 1. The difference between this and this is the quantity that has been collected here as condensate. The brine comes from higher temperature, Bi and Ti, and This is a lower pressure, lower temperature stage. So flashing is going to occur, some vapor is going to rise up, and the brine is going to cool down from capital Ti to capital Ti plus 1. So again, Ti is greater than Ti plus 1. Or we can put it this way, that Ti minus Ti plus 1 is delta Ti, or the temperature drop across the stage. In one through system, please note that we are using the brine, which is being flashed. We are using the temperature, capital T. For the distillate, we are using capital T also, but with subscript V. And for the seawater that comes into the unit, we are using the small t. So this is some sort of a difference in terminology that we are going to use so that we can differentiate. Do we mean the temperature of the brine, which is being exposed to flashing, or the temperature of the seawater, which is being preheated here? When we see this, when you are able to look at this kind of mass balance, it's easy to write the conservation of mass, and it's easy to write the conservation of energy as well, because now we see the whole picture clear in front of us. This is the brine heater, where it is going to receive the feed, the m dot feed, at a temperature small t1 and salinity xf. It will enter inside the tubes, where it will be heated by transferring heat from the steam, which is coming as saturated vapor, and it will leave as saturated liquid, so that the seawater will be heated from T1 to T node, which is the top brine temperature. This is the terminology used for the maximum temperature of the seawater leaving the brine heater, top brine temperature. These are the kind of assumptions that we are doing here. We are considering these assumptions for simplicity in the analysis. Specific heat is assumed to be constant, not a function of temperature, not a function of the salinity. Is it? Yes, but it's not a very strong function of them, so it does not change substantially with changing temperature and salinity. We assume equal temperatures drop for every recovery area, which means that the temperature change here is basically small Ti minus small Ti plus 1. This is a constant difference, which means that the delta small Ti is going to be the temperature difference across this stage, and the same temperature difference across the next stage and the next stage. See that this value is 3. So if this here is 37, then it will leave 3. The next step, it will leave as 46, and so on. So the delta T is fixed here. The same thing applies for this delta T. If the value is 3 also, then if we assume that this value, for example, is 45, then this is going to be 42, and so on. Latent heat vaporization in each stage is assumed to be constant. Instead of accounting for how the temperature varies in every stage and calculating the corresponding HFG, we are going to assume that we are taking an average value of the HFG at the average temperature of the whole states and taking it as a constant. Is that accurate? The answer is no. The question is, if it's not accurate, why are we doing it? The answer is because that makes it a little bit easy in the calculations in the model. And it's been tested that when we do that, the error is not significant, which means that we are just making our life easier, and we are not getting a big discrepancy from what the actual plants are performing. And accordingly, it has been accepted like that. Why is that? Because at that time in the 80s, people used to use their hands for the calculations and maybe the sliding ruler or so. The calculators were rather new. But that does not need a calculator. If you are going to account for variable properties, the CP is a function of temperature and salinity. The HFG is a function of temperature. And the same thing when it comes to the rest of the properties, then you would have an issue here that you need to be programmed. You need to write a program for it. Programs and computer usage was not that significant. And the issue is, practically speaking, why should we worry about writing a detailed program if you are able to get a simplified model with good accuracy? So that's probably something that you would need for research, but for running every day, or even sometimes when you are doing it for the design, if you are designing a unit, say that you are designing a heat exchanger, and we use the most accurate ways of property variations and so on, and you calculated the surface area to be, say, 80 meters square. When you are going to build the unit, you are going to make it 100. So what's the point of making it precise if you are going to increase it anyway? Why should we increase it? Any answers? Any clues? Do we need a factor of safety when you are making a thermal design of a heat exchanger? What do you think? You are designing a unit, and the precise calculation said that you needed 82 square meters of area, heat transfer area in your heat exchanger, but you said I'm going to make it 105. Why is that? You are increasing something like 20 to 25% of the area. I'm not sure, but I probably have mentioned something like that earlier.
Maybe due to the ambient condition that you cannot be sure about the ambient condition in all seasons.
This is a part of the answer. I mean, partially I can spend some time from day to day, but that is not the main reason. The main reason, Ibrahim, is when you think about it, you have a new heat exchanger. It's going to overperform for the first few months. After that, fouling is going to increase a little bit, although you might be using antifoulants, chemicals. Antifoulants reduce fouling, but that does not eliminate it. Scaling may start to occur. What do fouling and scaling do? They precipitate on the surface of the tubes as an insulating material, and then the unit performance becomes less. So you are over-designing by using higher area so that after a year, the unit is going to perform according to the designed condition. You don't want to shut down the unit after 1 year for maintenance. You need to make the shutdown every 2 years so that you reduce the downtime. So your solution then becomes, let's increase the area by a certain factor. They agreed something like 10 to 20% is fine, and that takes care of this. In heat exchangers, it's not only due to this, but in heat exchanger, it is common that you have some sort of a problem for a single tube. So you block it. So sometimes you make extra tubes in the heat exchanger so that when you block the tubes, still the original performance is not affected and it still performs well. So it's not a scientific reason, but it's basically some sort of an engineering practice that would make people build experience and then act based on the experience that they have. We are neglecting the effect of the non-condensable gases in the heat transfer process, neglecting the effect of the boiling point elevation, non-equilibrium losses on the energy stage or the energy balance for the stage, but we're going to retain them when we are talking about surface areas. So the assumptions here would be that these kind of losses, we can overlook the losses when it comes to the energy balance, but when we are calculating the heat transfer area, we are going to consider these losses as a part of our calculations. And you will appreciate that when you see the equations that are making the energy balance, and you'll see that, yes, we better do that. We better neglect the losses in the energy balance. Elements of the model include mass balance, for the water, mass balance for the salt, energy balance or first law of thermodynamics, so that we can come up with temperature profile, condensers and brine heater analysis, the condenser tubes in every stage, the brine heater, which is nothing but a shell and tube heat exchanger. They are going to be analyzed. We're going to look at the stage dimensions, and at the end, the same kind of performance parameters we'll be looking at. That is, what is the performance ratio of the system? What is the value of a specific heat transfer area? And in addition to that, something like the recovery ratio. To produce 1 kilogram per second of distillate, how much feed water that we have used? So that's basic, or you can put it this way, the ratio of the feed water to the distillate, or vice versa, out of the feed water, how much distillate that we could get, which is m dot distillate over m dot feed, which is a recovery ratio. The balance that we have here, the material balance, we have seen that in a while ago, that m dot feed is equal to m dot brine plus m dot distillate. When you look at the whole plant as your control volume, what enters to the unit? You have feed coming in, m dot feed. It is going to go through several processes here, from heating to preheating to heating again to flashing and flashing. And at the end, what are we getting? We are getting rejected brine and we are getting distillate. So the feed that has entered has been split into sweet water, and which is free of salt, and rejected brine, which is very rich in salt. And this equation is there. This equation is with us since we started the single effect evaporation. And if you are going to multiply each parameter with its salinity, then xf m dot feed is x brine m dot brine. So it's a typical equation that you put it in every system that we have. Now we are going to get to something unique about the MSF, which is this. The delta T per stage is equal to the top brine temperature, T naught, minus bottom brine temperature, which is Tn. This is the temperature of the brine that will be rejected to the sea at the last stage, divided by N. If the top brine temperature is 90, then this value is 90. Typical value of N, Tn is 40, divided by the number of stages. It will tell you how much is the temperature difference for every stage. And by the way, the expression T naught, top brine temperature, minus bottom brine temperature, this is what is referred to as the flashing range. In the first stage, the temperature is going to enter to the stage at a value of T naught, top brine temperature. It will reduce by a quantity of delta T and it will leave as T1. And then it will enter to the second stage. It will lose another value of delta T and it will leave at T2. So if we needed to get some sort of an expression of T2, it will be T1 minus delta T, or it will be T naught minus 2 delta T. So T2 is T naught minus 2 delta T. T3 is T naught minus 3 delta T. Ti is T naught minus I delta T. Well, that's good. So we can get some sort of an expression that will tell me what should be the temperature leaving effect number I. If I is equal to 10, so it should be T naught, top brine temperature minus 10 delta T. That's simple now. I can know the temperature everywhere. But remember, this is based on the fact that you are assuming that delta T is fixed. Now, let's look at the energy balance here. And that would be interesting. Here in the first line there, we are just looking at what is the energy in and what are the energy out. energy into the unit. The distillate flow rate here is N. So this one is inlet, sorry. Which is this. So it is a mass flow rate of the distillate here multiplied by its enthalpy. What is the enthalpy here? It is basically Cp into the temperature, and it is a distillate, so it's at a temperature TVI, where TVI is basically Ti minus boiling point elevation. What else is going in? It's the brine. Here it's entering at Bi. This is the rate, the flow rate of the brine. Its enthalpy is Cp into Ti. What else is entering? This is entering. M dot feed into Cp into Ti plus 1. So these are all energy into the system. Here, this one is positive. This one is positive. If we bring this to the other side, it will be positive. So this is energy in. What's the energy out? Distillate that has increased a little bit into its enthalpy, Cp into T vapor of I plus 1, brine, Cp at Ti plus 1, and m dot Cp, this is also leaving at Ti. So this one, and this one are, if they all brought to the left side, it will be by the minus side. Then let's do the assumption that we talked about, that we are going to neglect the effect of boiling point elevation here, and we are going to assume that TVI and Ti are equal. If this is the case, I can take CPTI as common, and then Bi plus sigma Di will be taken in the bracket. The same thing applies here. Cp into Ti plus 1 is common, and we have Bi and sigma Di plus 1, Bi plus 1. The right-hand side, it's basically m dot feed. The mass flow rate is not changing here. Cp into the temperature difference. There's something interesting here, because as we are going from one stage to the other, what increases and what decreasing? This distillate is increasing, isn't it? We're, say, having 1.5 kilograms from here, and then 0.5 will be added, so it will be 2 kilograms per second leaving here. This half, where did it come from? This is what this has lost by evaporation. So the B decreases, where the D increases at the same quantity. Where both of them came from? They came from the m dot feed. So this quantity here is nothing but m dot feed. And this quantity here is nothing but m dot feed. So I have m dot feed Cp Ti minus m dot feed Cp Ti plus 1 is equal to m dot feed Cp Ti minus Ti plus 1. Accordingly, if this is the case, I can divide the equation by m dot Cp. Now you can see how useful is it, our assumption that we are neglecting the effect of TBI, of the boiling point elevation, I'm sorry. Accordingly, we have Ti minus Ti plus 1 is basically Ti minus a small Ti plus 1. So delta T here is equal to delta T here. Accordingly, this is useful in predicting the temperature anywhere. If I know what is the feed temperature, I can calculate the temperature at any location here between stages of that seawater which is coming in. And that's another benefit, that before doing detailed analysis, you can just come up with all the temperatures that you want here. It's approximate, yes, but it's a good approximation. So delta capital T is equal to delta small t. Accordingly, T1, small t1, which is basically, if this is the whole flashing range, the temperature here enters at Tf. Here it will be Tf plus delta T, Tf plus 2 delta T, Tf plus 3 delta T, Tf plus 4 delta T, and here this one is going to be Tf plus the number of stages into delta T. Okay, so I can know the temperature at any location here inside these tubes. So I know the temperature at any location here, and I can know the temperature at any location here, which is interesting. Accordingly, I can get, if the temperature, what about the temperature here? What would it be? One way to get the temperatures by this. What's T2? It is basically T1 minus delta T. What is T1? T1 basically is TF plus N delta T. So I'm putting TF plus N delta T plus N delta T. So T2 is T1 minus delta T. T1 is TF into N delta T minus delta T. So it becomes TF into N minus 1 delta T. Here is it. To generalize it, Ti at any location at any stage is Tf plus N minus I minus 1 delta T. So it's a generalization where you can get the temperature anywhere at a single step. If I want to know the temperature entering the heat recovery of stage number 11, I don't have to look at stage number 1 and then 2 and then 3 and 4. I can just do it in one step like this. Then we come to the analysis within the stage. If we are talking about a certain stage here, and in that stage, what's happening here? The kind of temperature difference, the kind of enthalpy increase for the flow here, which is coming as m dot feed, it is going to gain a certain quantity of heat, which is equal to m feed into Cp into delta T. This is the energy added to this stream here. Where is it coming from? It's coming from rejection or condensation basically of the vapor. So this quantity of vapor has condensed to produce an increase in the temperature of the feed which is coming here. And hence we have this equation. Then we need some sort of a simplification in which we are going to divide the equation by Cp delta T, so that m dot feed, or let's divide it by HFG, so that m dot feed Cp delta T over HFG is equal to D1. And the Cp delta T over HFG, we're going to call it Y. It's a ratio between latent or sensible to latent heat. So D1 is Y into m feed. What about D2? D2 is Y of the quantity which is going there. In stage number 2, D2 is Y into the feed minus D1, because here, if you are talking about m dot feed coming in here, what will come in here will be m dot feed minus D1. And what will come to the next will be m dot feed minus D1 minus D2. And then m dot feed minus D1 minus D2 minus D3 and so on. So that's something that you can calculate here. The D2 is going to be Y into m feed minus D1. And D1 is basically Y into m feed. So basically what we get lately would be Y into mf common 1 minus Y. It can be generalized. Actually, it's written here for 3 stages, but it can be generalized to have basically the Di by that expression Y m dot feed into 1 minus Y to the power I minus 1, which means that I have a plant which is having 24 stages, and then I can ask you what will be the quantity that should be formed, the vapor that will form in stage number 17. You don't have to do complicated analysis. You just need to come here and see, fine, I know what's the value of delta T, which is T naught, minus Tn divided by n. And then I should know what is the value of the Cp for the water. I should know the value of HFG. Then I can calculate the value of Y. Once I know the value of Y, what I'm looking for D17. So I is equal to 17. Substitute I is equal to 17. Knowing the value of m dot feed, then you can get your value of Di. This is the distillate at stage number 17, for example. Then what about the total quantity of distillate, m dot distillate? This is the total, which is D1 plus D2 plus D3 up to Dn. Then this is going to be generalized, as you can see it here. You can follow it one by the same manner that we've done earlier, and you can get the value of m dot distillate here. This is the total quantity of the distillate related to the feed and the sensible to latent heat ratio and the number of stages. Oh, that's something new here, because previously we used to obtain a relation between m dot f and m dot d as m dot d plus m dot b, and you obtain that with the salinity. This is an alternative now, that I don't need to know much about the salinity. I don't need to know much about what is the value of m dot b, but I can establish another relation between the distillate, total distillate formed, the feed, the sensible to latent heat ratio, and the number of stages. Then you can get the total quantity of distillate. And sometimes we do problems where the trick of the problem is related to this. For example, I would tell you that I have a plant which is producing 20 kilogram per second, and it is made up of certain number of stages, for example, 20 stages, 24 stages, and the CP is 4.2 or 3.8, it depends. The delta T, I would give you the value of top brine temperature and rejected brine temperature, so that you can calculate delta T, and you're going to estimate the value of HFG. Then what's the value of m dot feed? Or I don't give information about the salinity of the water which is being rejected, for example. I just hide it. And I ask you to do some calculations where you definitely need the value of m dot feed. How to obtain it? You can rely on this equation to obtain the feed flow rate then. The brine here, that's another interesting thing, because if we're going to talk about the first stage, in the first stage, what is entering is m dot feed, or part of it is being converted into vapor, and what will be leaving is B1. So B1 is m dot feed minus D1. B2 is B1 minus D2, which is m dot feed minus D1 minus D2, and so on. So a general relation between BI and m dot feed can be given in terms of the quantity of distillate which is being formed. And the balance is being done here. For every stage, Xi Bi is constant. So X1 B1 is X2 B2 is X3 B3 is XF MF is X brine M brine. So that's basically the kind of salt balance that we are getting in every one of the stages. Now, when we look at this, then you can estimate almost anything without having to do detailed analysis of the plant. All what you have to do is just use this kind of recurrence relations that we are developing, and you can get the estimate of the quantity that you want, be it temperature, brine flow rate, brine salinity, distillate flow rate, temperature of the brine, temperature of the feed, whatever. You can obtain it all without having to analyze every one of the stages. You don't need to solve simultaneous equations to do that. Where this all originated from? It originated from the energy balance, where we neglected the effect of boiling point elevation. And we said that we are going to assume T and TV are the same. So you can see such a small assumption that we have done in the unit at the beginning has led to a great simplification in the whole program so that you don't have to solve system of equations to do it. It is not accurate 100%, yes, but it's still affordable. You can do the calculations, what we call it as back of the envelope calculations. That's something that you can do easily without having to write a whole program for. You can just obtain any value in a step. The brine heater, nothing is new here. It's a heat exchanger where we have seen this analysis before. The steam which is coming to lose its latent heat, this latent heat which is lost, is used to preheat the feed from T1 to the top brine temperature T node. And if this is the temperature distribution inside the brine heater, this is the temperature of the steam, then it is used to heat the feed from T1 to T node. So this is delta T1 right here, which is terminal temperature difference on the hot side. This is delta T2, and then you can calculate the log mean temperature difference accordingly. And some of the work that has been done substantially in the literature, and it has been used to calculate the overall heat transfer coefficient as a function of the temperature. I remember in the last homework some of you have used this expression to estimate an unknown temperature or so, if I can remember. And then for every stage, here in this condition, we cannot neglect the effect of the boiling point elevation. If I'm talking about a single effect here, a single stage, stage number I. In this stage, there is water coming here, m dot feed, and the temperature is Ti plus 1 into Ti. And there's vapor which is formed here, which is basically the quantity is Di. So when I'm looking at the temperature profile here, the temperature here is Tv. And this Tv basically is Ti minus boiling point elevation. So here I'm going to account for the boiling point elevation. This is where the temperature increases from Ti plus 1 to Ti. Then I can calculate the thermal temperature difference of this stage, and then I can calculate the log mean temperature difference for this stage, where basically I'm relying on the vapor temperature, which is less than the salty water temperature by the boiling point elevation. And the same expression I used earlier for the calculations of the overall heat transfer coefficient can be used here. You can do that for every stage, or you can assume that you have a constant area so that you will calculate the area for one stage and multiply it by the number of stages. Then you can come up with the total surface area that you would need in your plant. Area of the brine heater plus area of the condenser tube in one stages into the number of stages. This will give you the total surface area that is needed for your system. Then we end up with some additional geometric information that are needed, which are basically the gate height, the height of the brine pool, the width of the stage, the length of the stage, and so on. Actually, it's some of them have typical values. Like when we are saying here that the brine pool height is greater than the gate height, what I mean here is if this is the stage, or let me put it this way, you need a reduction in pressure. So the brine is here lifted up to a certain level, and you have a gate height here. This is where the brine is going to leave into the next stage. The gate height is to be calculated, and the brine pool height is greater than the gate height by about 20 centimeters. So it's a typical industrial value here. And here are some information related to the stage dimensions. GH is the gate height, and the gate height is having an expression that can be used to obtain it, which is, you can see it here, that's m dot minus sigma di, which is basically the brine located at this location, into It's something like an orifice kind of equation where the coefficient of discharge is given, and this is the width of the stage, and this is the delta P across the stage, how much pressure loss across the stage. Rho is the density of the brine. So here you can calculate how much would be the gate height. Delta P is the pressure difference or pressure drop across the unit, and then density, wear coefficient, stage width, which is basically the flow rate divided by the velocity of the rising vapor. MF is the feed flow rate, and this is the brine mass velocity per chamber width. And then the brine pool height is greater than the gate height by about 20 centimeters, which is some sort of an acceptable practice for the design of the unit. Length of the last stage can be calculated here as the brine leaving the last. I mean, the equation that we see here, this equation is nothing but a conservation of mass. Basically, m dot is equal to rho into A into the velocity. This is what you see here. Rho into the velocity into width times the length is the area is equal to the mass flow rate at the last stage, which is dn. So it's a mass balance equation that you can use to calculate the length of the last stage. So we have the length here, we have the width of the stage, and the surface area of the stage is basically the length into the width, cross-sectional area, I'm sorry. Then at the end, what we'll be looking for is performance ratio, m dot distillate over m dot steam, specific heat transfer area, which is area of the brine heater, plus the area of all the stages, it's all divided by the distillate rate, m dot distillate. Then you can estimate how much would be the heat transfer area, specific heat transfer area needed for your plant. There's an example in the book, and this example is resulting in these values here that are estimating the productivity and the performance associated with every one of the stages that we have. Maybe you can take this as our inlet screen for our next class and start discussing the different values that we have here. That would be it for today. I would like to tell you that I'm expecting another progress report related to your project a week from today. So next Wednesday, I should expect some sort of a report that tells that you have done the analysis and you started to get some preliminary results. Maybe you can show me the results in a table form or in a figure form or whatever, but there's some sort of an evidence that I need to see that manifests the progress that you have done in your projects. So that will be a week from today, inshallah. Okay, thank you, and we'll see you next time, inshallah, on Monday.
Doctor?
Yes.
I think my partner dropped the term, so I'm alone.
Who's your partner?
Majid.
Majid Shehri.
Yes.
Oh, I see. So how about your ability to continue? Can you continue the project on your own?
Well, I need more time to finish it if I continue alone.
But the point is, can you do it?
If I'm alone, well, maybe I can finish it, but not on the time. Maybe 3 weeks after the end of the time.
Will it make a difference if we make you join another group, but you'll have to, the project will be different?
No problem, because I can manage to have a different task and read another topics. No problem for me.
Okay, so I just want you to look. Do we have the list of the projects, Ya Shabab, which is on Blackboard? If we have it, just look at it and have a chat with me first, Muhannad, before you take an action.
Okay.
Look
but
at the list and drop me an email, say by tomorrow, before tomorrow noon, for example, and tell me that this is the project I'd like to be involved in, and then we can try to find an additional task for you to do in that project.
okay. Thank you, Doctor.
طيب اوكي تمام. Any further